You can start whenever you want. Yep.
Oh, okay. Hi, this is Dan LaRouche, speaking for Group 4, Chen Shu and Dan LaRouche. And we're going to be presenting a paper uh, about 2D FQ, which is a queuing mechanism for cloud services. Uh, this was a paper presented by researchers from Microsoft and Brown University. And the paper examines the role of queuing in cloud, the problems with it, and their solution, which they believe is a better solution than what was currently in use 2 years ago when the paper was presented, or 3 years ago when the paper was presented. We're going to follow roughly the structure of the paper. We're going to talk about the role of queues in the cloud. We'll digress for a bit to discuss something called GPS, which is referred to in the paper but not described. So we did a little background research and are going to share that with you. And then we're going to discuss some of the queuing mechanisms that are in use today in the cloud. And then we'll look at the solutions presented and how they're evaluated and how the authors concluded their paper. And then we'll briefly critique the paper. Queuing in the cloud is fundamental. There are resources in the cloud, as I'm sure you're all aware. Some of them are processor resources, there are storage resources, there are queues that people use. And all of these resources can be overcommitted. So rather than directly calling these resources and then not being able to get them, tenants or customers submit requests for these resources. And it's critical that customers get the resources they have paid for. It's critical that they get them in a timely fashion. If somebody's running a website and they get stuck behind long-running processes, that's really bad, and that customer or tenant may leave or complain to management. So it makes sense that Microsoft was very interested in finding a fair queuing system that would keep their customers happy. And we believe that was a big part of the motivation for this paper. And here we discussed briefly in one of the previous bullets some of the services that are used. GPS, as I mentioned before, is an ideal model that this paper is going to refer to. It's based on continuous processes that can be interrupted so they can be scheduled perfectly. And the idea is it gives every customer exactly what they've paid for. But it's a goal. And here's an example of how it might work at a very high level. We have 4 customers. One of them has weight 1, meaning they've paid for 1 resource, is a way to look at that. The next one has weight 2. They've paid twice as much. They want twice as much resource. And then we have customer 3 and customer 4. And when they get into the queue over here on the right, you see that they get exactly the percentage of the resource that they've paid for. The only exception would, of course, would be if one of the customers had no requests in the queue, then everybody else would get more of the queue because there's free resource. So let's go on to the next slide. Unfortunately, most of the work in the cloud is done in discrete, uninterruptible chunks. So this GPS model isn't really going to work exactly. But it's still a goal. It's still what we're trying to get. We're also trying to get 100% utilization because cloud providers like Microsoft want to get use out of all of the resources they are providing. Most, or I guess the most common solutions presented today are weighted fair queuing and worst case weighted fair queuing, which are attempts to approximate GPS. So let's look at them in some detail. Weighted fair queuing relies on the estimated job completion time. And of course, because it's an estimated job completion time, it can vary from the real completion time, which is where we can get into trouble, or one of the ways we can get into trouble. And we're going to correct estimates, but if we correct the estimates after the jobs have been completed, it may be too late. And here we have how the job completion or job finish time, as it's called here, is calculated. I'm not going to go through it in complete detail, but I think the key thing to look at is this concept of virtual start time and virtual finish time, which are in the end queuer's own timeline. Or so in the end queuer in this case would be the customer, or the tenant as the paper refers to them. So what they're looking at is for each customer of a cloud service is queuing requests. And if we imagine that customer in their own virtual isolated container, what would be the estimated finish time? And that's what's being calculated here. And then WFQ very simply just selects the pending request with the lowest virtual finish time. And that's the one that gets executed next. So let's take a look. Here's an example. The example is right from the paper. It assumes a resource that can process 2 threads or 2 requests at a time. And we have a chart that shows the calculation for virtual start and finish time for 4 tenants or 4 customers. The customers are A, B, C, and D. And we see the requests, and what's most critical is their virtual finish time. What you can also see when you look at this is customers C and D are submitting large requests, and customers A and B are submitting small requests. So the first 2 requests to be executed are the ones with the lowest finish time. That's A1 and B1, and they go right in. They're executed first. After they're executed, we go on. What are the next 2 to be executed? B1 and B2. And then you see B3 and A3. And then B4 and A4. And then when we go to the next slide, we see finally D and C get in. And then we keep repeating this process, and we get this rather troublesome dequeuing, where A and B are running along very happily, and then C and D get in and block them for a long time. Then they run along very happily again, and then C and D get in again, and this can repeat. So let's take a look at the next slide. WFQ has a worst case example, which is an attempt to improve it. We're going to see it doesn't really make much of a difference in the case we just looked at. The WFQ2 works exactly like WFQ. I'm sorry, I should refer to it as worst case fair queuing. It uh, it attempts to delay large requests that from monopolizing the system by looking at their virtual scheduled time, and it will only display will only execute requests if the current time is less than the virtual scheduled request time. So let's take a look at how that might work. Here we have the same requests as we had in the previous example. And we start off exactly the same because we look at the scheduled start time for the 4 requests. And they're all 0. So they're less than 1, which is the current time. But then when we get to the clock time of 1, real time, we see that A and B no longer have any valid requests because their scheduled start time is 1, which is not less than the clock time. So we pick up C and D. And we go on to the next slide. And then using the same algorithm, we pick up A and B again. And when we're all finished, we have a dequeuing algorithm that looks almost exactly like WFQ. So in summary with WFQ and worst case WFQ, we're going to compare what the authors think is a fair model, which is the first picture you see up here, where the big requests or large requests would have gone on their own, sharing their own thread, and the small requests would have had a fairly steady dequeuing. The aggregate, the end result is all the requests are serviced in the same total time, but it's a smoother response time for each enqueuer. The second 2 examples show the bursty example, and the final picture wasn't really in the presentation, but it's something to show what could really go wrong. Think of jobs where some math professor says he wants to set a world record for calculating pi and submits a job that's going to take days. And if you have a few professors doing that sort of thing, all your queues could be very busy and with very large jobs, and the little jobs could get blocked out completely. So we're trying to avoid that. And the way the authors tried to solve that is they introduced really one new queuing algorithm, and it has 2 variants, and they called it 2-dimensional fair queuing. And we have the first model, which is for known request sizes, and then the second model is a variant of that when we don't know the request size in advance. So I'll let Chen describe 2DFQ for you.
All right. Thank you, Dan. 2DFQ, which author referred the 2-dimensional fair queuing. The main idea is to create a smooth schedule or queen to deal with the expensive and the small requests. So the the 2DFQ attend to schedule small requests to a high index threads, which is like here, like on the top, and expensive one on the bottom. In order to do that, 2DFQ is basically the same as WF2Q, but with some small changes. Like for one, is a request can be eligible to all threads. This let's go back. Uh, you see the example of WFQ and WF2Q. The problem is B and D always scheduled to thread one, and A and C are always scheduled to 0. So in order to avoid that, they break the bond between customer and the thread, so they can share every thread in the in the workload. And also, they modify the eligible time for each thread using the equation below, which basically the main point is it involves the request length. So it's what they do is when the request getting larger, the eligible time for every request for long request getting lower on the low index threads. Here is an example, like for A1, the start time is 0, and for thread 0, because the I stand for thread ID, so it's 0 over 2 times 1, so it's 0, so it stays 0. But for thread 1, it's 1 over 2 times 1, so it's minus 0.5, so it's negative 0.5. All right, let's go into a animated demonstration. So at time 0, we have A1, B1, C1, D1 eligible. A1 and B1 have a finish time 1 in thread 0 and 0.5 in thread 1. C1, D1 have a finish time 4 in thread 0 and 2 in thread 1. So at time 0, we just schedule A1 and B1. And after we schedule A1 and B1, we go to the clock at time 1. The second request of A and B will not be eligible on like workload thread 0 until t equal to 2, based on the same reason Dan mentioned in before WF2Q. But they are eligible on W1 since we modify the eligible time for A2 and B2. So that's why we schedule C1 to thread 0 and A2 to thread 1. Okay, after that, when thread 0 is dealing with C1, the it is busy. So thread 1, so the 2DFQ keeps scheduling B2, A3, B3 in that. So that's what we get right now. And at this point, we have A4, B4, C2, D1 for the same reason we mentioned at here. We just schedule A4 and D1 in. That's basically it. So they continue schedule expensive requests to lower index threads. All right. So here is 2DFQE, which Dan will explain it to you in detail. Go
Okay,
ahead.
thank you, Chen. Thank you. Okay, 2DFQE, very similar to 2DFQ, with some changes for handling jobs where the request size is not known in advance. The first thing, as you would imagine, is it's got to have a way of estimating job sizes. And then it has a mechanism for correcting after the fact if its estimates are wrong. And they call that retroactive charging. So if they overestimate your job and they run your job and they think it's going to be a long job and your job comes in really quick, you get something back so your next job can go a little faster or a little sooner. And the reverse is also true. And then finally, they have something called refresh charging. And that's a way of checking requests while they're running for in cases where customers have variable requests and they suddenly send a bunch of requests that are very large. You don't want them all to get in before you figure out that the customers changed their pattern. So it's a way of slowing things down when you notice that the requests are very large and not without waiting for them to finish. And we'll see these briefly. Let's go on and look at the next slide here. Okay, for the estimate, 2DFQ uses something called a pessimistic estimate. They basically they take the largest request they have seen for a customer, and that's their starting estimate. And then each time a request completes, they reduce the estimate by a very small fraction. They don't specify the fraction. They specify the algorithm, but the key is that it's reduced by a small amount and you can tune that amount. So if the biggest request the customer submitted is 4, that's the estimate the first time for the next request. And then the request after that will be a little bit less than 4, and then it keeps dropping until they see a bigger request, and then the estimate suddenly jumps back to that bigger request. That's pretty much all there is to estimates. Retroactive charging, if you remember, is for dealing with requests after they're complete that didn't fit the estimate. And what it does is it looks at the delta, whether it's a negative or a positive, and it tries to issue a refund to the customer. And the way it does that is it adjusts the virtual start and finish times of subsequent jobs based equal to the amount of the delta between the actual size and the estimated size of the job. Refresh charging is interesting to me anyway. That runs periodically, and it looks at jobs while they're running or requests while they're running. And it says if a request that is running has run past its estimated time, it has to do something to prevent more large requests from getting in. And it adjusts the estimated completion time. I'm sorry, it adjusts the customer's virtual clock forward by the delta of not exactly of the time that it's overrun the estimate, but it's the time it's overrun the estimate or since the time it's overrun since the last refresh charging interval, because it doesn't want to double charge somebody each time it runs refresh charging. So to make that clear, the first time it runs refresh charging, it sees the customers run 3 units over their estimated time. It adjusts by 3 units the virtual clock for that customer. Now it runs refresh charging again. Well, and let's say it sees that the job is run an additional 3 units of time. It only charges for those additional 3 units, not the full 6 units over the estimated time. And that's refresh charging. And that's the end of 2DFQE. And I'll let Chen take you through the next section.
All right. Author explained the theory, as we mentioned before, and they also did some evaluation about the about this algorithm compared to the existing ones. Here are some general setups for the evaluation. Worthy to mention is 2DFQ and 2DFQE are experimented separately with different workloads. We will mention later. And also, please take care of the evaluation factors, which the article used to evaluate their experiment results, like service lag variation, service rates, latency, and Gini index. They're all combined to getting a performance of the algorithm. For the non-request cost, which is used to test the 2DFQ, the workloads are composed as below. Like the synthetic one has 100 backlogged tenants with 16 worker threads, and also they have n small tenants, which means 100 minus n expensive tenants, and also because they are synthetic, so the small and expensive tenants request size are based on normal distribution. And also they have production workloads, which is just taking out from actual server, and they have the following setups, which situation become more complicated. We'll talk about later. For the synthetic workloads experiment, you can see the first two graph are for one tenant in the experiment, and the red line in this picture indicates the 2DFQ efficiency. So you can see here, 2DFQ certainly have less oscillation, means their service is provided more smoothly, which that's what they want. And also in the middle, it shows virtually the light color means the threads are working with lights request or a small one, and the dark color means they are expensive. And this one means because we mentioned like there are n small requests and 100 minus n expensive requests. So these are just saying um, showing like when the expensive tenants grow, how the service lag will change. As this line here, you can see 2DFQ is still doing better than other two. For the production workloads experiment, basically these two are the same. It's coming from one thread, one tenant. So you can still see like the red has basically more stable service overall, and this is just the previous picture become more complicated, and also they do uh, like a cross compare between different tenants, so you can see the service lag change between different tenants, and also the cumulative frequency across all the experiments. All right. Now the 2DFQE part is Dan's part again, so let's hear him. All right.
Okay. Um, in 2DFQE, again, two tests were performed. First, an experiment where they examined a single workload in detail. And second, a suite of different workloads derived from production workload traces. And they looked at overall service lag and request latency. Um, in test one, which is the experiment, the WFQ provides service with the most oscillations. So big surprise, they found that was the worst. Worst case WFQ, which is supposed to be an improvement on WFQ, had service with occasional spikes, and 2DFQE provides consistently smooth service. So they found what they expected. They said in all but one case, 2DFQE improved latency. The single case where it did not was a customer that had expensive and unpredictable requests. Um, the paper throughout is said their goal was really to provide smooth service to the customers with small requests. They felt that the customers with the large requests don't really need the same level of consistency that the other customers do. By their very nature, large requests usually can tolerate some delay. And we'll talk a little bit more about that at the end as to whether that we feel that's valid or not. It's certainly a judgment call, but we'll talk about it. Um, they have some results here. You can read the graph for yourself, but I've summarized what it says in the previous slide. Test two, they found, again, good results, not surprising. I think if they didn't, they probably wouldn't have presented the paper. So they found 99th percentile latency improvements. Some customers that did not see latency improvements were customers with large and or unpredictable requests, very similar to the experiment. So this was not an unexpected result. And then they found, I think, an interesting tidbit. As the unpredictability increased, then 2D FQE's advantage increased. So that's certainly worth noting and worth further study. And we can look at the graphs here. One thing of note to look at in these graphs is, although they do present a good case for 2D FQE, it's not as clear cut as it was for 2D FQ. So it's something to keep in mind when thinking about this. And I'll let Chen take you through the next section.
All right, thank you. Here is some conclusion about the evaluation. Like, 2DFQ reduces 1 or 2 magnitude service lag variation for all small and medium tenants, and also maintain a very low service lag variation when there are a lot of tenants have expensive request queuing. And also 2DFQE provide the same low service lag variation, also improves the tail latency for predictable tenants by about more than 100 times, and for uh, also improves the 99th percentile latency for predictable tenants by up to um, one around 200 times. Mm. Besides the main article about theory and experiments, author also mentions some limitations and alternatives, such as work conserving schedulers in general cannot improve service when the system is underutilized. So, what does that mean? Is when the system is dealing with a lot of expensive requests, there are no room for small requests to sneak in because they are work conserving, which means they have to keep busy doing everything. Like, they have to keep every thread busy. So they provide some solution for that, which is stop using work conserving, or either allow a variable number of worker threads to or ends to spawn new threads when small requests show up, which basically means either you keep some threads idle, or you create new threads when small requests just show up. Or they also discuss about the possibility of you can cutting expensive requests into small ones, so make them can be scheduled more smoothly. But right now, it seems very hard to achieve. Um, After that, after reading all the paper and doing the PowerPoint, we have some opinions of our own. Like, is there really a problem with queuing in the cloud? Obviously, Microsoft consider it as a problem for sure, or otherwise this paper won't come out. And we also find there are some other research for the same topic like out there. If you guys interested, you can find them. And also, this article presents a very clear and logic case for us to to believe this is truly a problem. And are the stated goals appropriate? Um, I think they're. I think this certainly they are very good for customers with like their requests are mostly small because they can be scheduled like really fast and dequeuing very fast. And also I think it's doing okay to the large request, but yeah, we have some doubts, but this seems good, and we don't really know how good it is when the customer is sending mixed requests, like one small, one expensive, stuff like that. And also, does the 2D FQ offer a fair solution? Yeah, we think most mm, I'm sorry. I think the 2DFQ logically is or theoretically is a good idea to separate the small requests and expensive requests into two queues, but we also find like the testing could be done more because we have seen during our research we have seen many applications have like variable processing for end of day, end of week, or peak days, something like that. So the experiment results of this paper seems too small to capture all the data we want. But but with that, we still think the 2DFQ appears to be a very a great improvement over WFQ and WF2Q. And also, does 2DFQE offer a fair solution? Similarly, we think theoretically it's good, but the testing is not enough to show a lot to us. But what we can say is that it's still a proof for, but we need more data to make it more convincing. All right. So, what's the overall opinion? It is worth a try. It's likely to succeed, but more evidence is needed, and more research into what is fair is needed. Which means right now we are not sure from the article that this is the true solution or the one. All right. Okay. So yeah, that's basically wrap everything, and thank you for watching. Have a great day.